So, the first algorithm which we are going to study in this grid based path planning is breadth first graph traverse algorithm, and first we will apply will apply this BSF algorithm to any general graph with some nodes with some edges, and then we will apply the same algorithm to our grid based environment, okay, which is our actually goal um, to study how we can apply this different path planning algorithms to our robotic environment, which is split in the grid cells. So, let me take this example, which is has nodes starting. Let us say this is our starting node, and just to understand this BSF algorithm, we have the starting node. We can have any starting node, and then we our goal is to explore all the nodes in the environment, to explore all the nodes in the environment. So, let us see how this algorithm works. So, this is, you see that this is the directed graph type of the graph algorithm. Sorry, this is directed graph algorithm, directed graph, because we have the edges which can go from A to C, but we cannot go back from C to A. Similarly, we can go from E to F, but we cannot go from F to E. So, this is the example of the directed graph. So, to start the algorithm, we have to initialize two variables. Two variables, one is the one variable that we call it the visited, and second is the queue. So, these are two variables when we write the code, for example, in Python or C++. So, first we define two variables, we can give any name, but let us say the visited and queue, and we we put the first starting node. So, in this case A is our starting node. So, we put this starting node in the visited list. So, these are two lists, right. Then in the this is initialization. After that, in the step 1, we see the connected nodes with starting node. So, in this case, in this example, we have two connected nodes which are nearby to this node, which are node B and C, right. So, what we do here, we okay. So, first these two lists, we put the starting node in the visited list and also in the queue list, and then we remove the visited list, because we already visited this list node A from the queue list. We remove it, and then we find the adjacent nodes of A, our current node, visited node. So, they are B and C in this case, in this example. So, after that, um, we find that these two nodes are the our next nodes which are not in the visited list yet. But when we see, also we check the visited list, so in visited list there is no B and C. So, we think that these two nodes are the new nodes which are just we exploring it, explored it, right. So, we put these new nodes B and C in the visited list now, and also in the queue list. So, these are the in this case the B and C are the newly explored nodes, and we put these nodes in the both lists, visited list and queue list. After this step, we uh, we go back to the next step. Again, we go to the next step, and we see remove the leftmost node in the queue list. So, here this is our queue list. So, then currently in the queue list there are two nodes B and C, and we remove this leftmost node from the queue list in the next step, and then find the adjacent nodes to that removed list, as we did in the first step. In the first step, we removed A from the queue list and find the adjacent nodes to A. So, in this case B and C. Next, we remove B. So, find the adjacent nodes of B. In this step, we remove the B from the queue list and then find the adjacent nodes of of this node B. So in this case, in this example, we have these nodes of B, D, and E only, and we check that D and E are not in the visited list. So we add them in the visited list, and we also add these nodes in the queue list. So we keep continuing the same way. We remove the leftmost node in the queue list, which is C in this case, and find the adjacent nodes to C. We remove C from the queue list and then find the adjacent nodes of C. In this case, these are F and G nodes, and we check that F and G nodes are not in the visited list already. So we place them in the visited list, and also we place them in the queue list, and we continue. Next, in the next step, we remove this D because this is leftmost node in the algorithm in the queue list. So remove this out and find the adjacent nodes of D. So in this case, we are here D. So there is no adjacent node to D because this is in this example, D is the last. If you go back over here, so D is here. So you see there is no adjacent node because this is a directed graph. So it means that we have no adjacent node near to D. So we cannot put any new node in the visited list and in our. So we cannot put any node over here because there is no new list new visited list, and so we cannot put any new node in the queue list because there is no adjacent nodes to the D. There is no, right. Okay, but we remove D out of the queue list. Next node which is present in the queue list on the leftmost side is the E node. So we remove E from this node and find the adjacent nodes of E. So we see that adjacent node to E in our graph is H and F. So remove E from the from the list and see the which are the adjacent nodes to the node E, which are not in the presently not in the visited list. So only H is not present, F is already present. Okay, F is already present over there, but H is not present. So we add H in the visited list and also add H on the queue list and continue. Next, we remove the F node and see which are the nodes which are close to the F. So in this case, because this is directed graph, so there is no list. So there is no node close to the connected to the node F, which where we can go from F. We cannot go from F to any other node. So it means that there is no other node. So we cannot update our visitor list will remain same, and queue list will also remain same. But we remove F from the queue list. Our next node in the queue list is G. Okay, and it means that this G, and again we see that there is no node connected to the G. Let me see our original graph. So okay, we are here G. So after G there is no node. After G there is no node. So G is our last in this direction. So we remove G out of queue list. Okay, and there is no new list to add. There is no new node to add in this list. So our list will remain same. Visitor list will remain same, and our queue list will have only one node left. So that last node we remove from queue list, that is the H, and find which are the adjacent nodes to the H. Again, there is no adjacent nodes to the H where we can go from H to. We cannot go from H to any other. We cannot go. So it means that we cannot we cannot add any other node to our visitor list, and queue list will be empty in the last step. So when queue list is empty, we stop our algorithm. Okay. So this is the stopping condition. So when we start from the visitor list and then continue adding new nodes in the visitor list, and also removing the also adding the new nodes in the queue list, and also removing the leftmost node from the queue list, and until the queue list is empty. When queue list is empty, okay, we stop our algorithm. So now what you see in the visitor list, so in the visitor list you see the all explored nodes. So all nodes are explored. Explored mean that we have visited all the nodes one by one. So we this that if even if we have 100 nodes or 1000 nodes, if we apply this algorithm, BSF algorithm, it will go to all the nodes one by one. So it means that in the wish list we have all the nodes. So this is the graph traversal algorithm, right? So that traversal means that we traverse, we visit all the nodes in the graph in this algorithm. So in this, because in this example we don't have any goal node, but we can stop. We can, if let's say any node is goal node. Let's say this E is goal node, right? For example, if this is goal node, this is the starting node. So it means that when we reach the goal node, we stop our algorithm. So it means that the BSF can be used to find the goal node as well. So let's see how we can. Let me go to this example first. So this example of some nodes. Let's say we have 6 nodes here, which is the directed graph. Example of a directed graph, and how we can implement this in let's say Python. Okay, so this simply you can see this code, that first we make a graph using this list uh, using these lists. So it means that 5 is connected to 3 and 7, 3 is connected to 2 and 4, 7 is connected to 8, and 2 is not connected to any, 4 is not connected to any, and 8 is not connected to any. So this, we can create this graph, and so using this list operation, we can create any type of the node, any type of the graph. So then we we declare these two variables, visited and queue. So initially they are empty. We just declare two variables, and then let me define this our BSF algorithm. So what we have inputs, that we have the graph which we created over here, and the nodes we provide, starting node and then visited node. So then we append these node, visited and queue nodes with the current node which we are exploring right now. And in the while loop, we we remove the leftmost node from the queue node. Pop means that remove it, the leftmost node from that node, and then add uh, the next node which are linked to the m node to the queue list, and also the visited list. So if, for example, in this example, if we apply our 5 is a starting node, so this algorithm will call this function BSF and the graph which we have created over there, and it will generate a list of the all the visited nodes. So you can try it later. Another example I found, that okay, here this is again the BSF algorithm in Python. You create the graph first. So I think this graph is A, starting from A, then we have B and C, then from B we have D and E, and then from from C we have F and G, and that's all. I think this is the same example we did over here. This is the same example, and then there is E. I think this is F. This is G, and E is there is H here, and there is F here. Right. So this is same example. So if we create this, we can print this graph, and then we apply this algorithm um, in Python. So we can print this the list of the visited nodes at the end. So using this example, you can create any type of the graph, and then you apply this algorithm to apply this BSF algorithm. So let's apply this algorithm to our actual environment, which is the grid environment. And before applying this algorithm, let's we talk about a little more detail about the grid environment. So as we discussed before, that grid is just sorry. So we split our environment in the grids with black and white and gray colors. So dark or black points will show the occupied or maybe not free cells. White will show the free cells, and if there is a gray, it will show a not explored area. And then we starting point SP, starting point somewhere in the graph, and then we have some GP, goal point, in somewhere in this environment. And also we define the connectivity of this graph. The connectivity can be 4 connectivity, can be 8 connectivity. First, let's just keep it simple. Just to, let's say we do some example with the 4 connectivity first. So 4 connectivity means that we can move, if we are in any cell, we can move up, down, left, right, but we cannot move in the diagonals, and also we cannot move to the black areas, and also we cannot move in the boundary areas. So these are the conditions, right? So let me write down. So in a 4 connectivity scheme, can move up, down, left, right, and cannot cannot move in the black area, black nodes, and boundary nodes, because that boundary is, we cannot go outside that, we cannot go there. So we'll use this grid map, and in our next lecture, I mean the next lecture today, and also maybe next week also. So we'll apply this BSF algorithm, we apply the DEX algorithm, we apply the AST algorithm to this grid map. So as we said that this BSF algorithm is also called the Grassfire algorithm. If we have the terminal condition that when the BSF reaches to the goal node, so it will stop. So that is called the Grassfire algorithm. Otherwise, a BSF can be used to explore the full graph. But if we until it we explore all the nodes, but if we stop at the goal point, goal node, then it is called the grassfire algorithm. Why grassfire? Because the grass, if there is a fire in the grass, so the fire will spread in all directions, right? So that's why it's called the grass fire. Fire, you can see the fire in the grass, spreads in all directions. So that's why this name is given. Okay, so let's see more about the this grid. Let's we have this example, right? So this is the example grid. So in this we have some starting point. Let's say starting point is represented as a green node. There is an end node which represented is a red node, and then the white is free, black is occupied. You know already. So if we connect all these nodes which are free to go, or with destination and also the starting node with some dots, like this dot, yellow dots, except that the dark areas where we cannot go. So and then if you see this dots and with edges, so it is a graph basically, right? It is a graph. This we can represent this graph in any shape. Currently it is represented as horizontal and vertical, but you can represent it like this, okay, like this. You can write this. This is basically graph, right? So the same example that we did the first time. So this graph can finally this graph represented like this. But this is the special type of the graph that which is a grid based graph, where each unit is has each distance is 1 unit away. Sorry, each node is 1 unit away from the neighboring nodes. So this is 1 unit, this is 1 unit. But in general, in graph, this can be different. This may be 2 kilometers, this may be 5 kilometers, this may be 3, this can be 1. Okay, but this in the grid based uh, graphs, they are special graph with 1 unit distance between the nodes. So we also call this grid based map in the robotics. We call it occupancy grid map. Occupancy means that some places which are occupied with some objects in the environment, and it is the graph is represented by the grids. That's why the name is given occupancy grid map. So for example, this is the factory floor example, right? So we can represent this any environment, your home or maybe your office, or any floor with this kind of the information, right? So we can first we split this in the grids, then the 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 dark areas will be obstacles and free areas will be white areas will be free. And then we can apply these algorithms to find the, let's say this is our current starting position of our robot. Now our robot want to go on, let's say this cell is our goal cell. Then we can apply this BSF algorithm or Dexter algorithm or A star algorithm to this grid cell grid environment to make a path between this between through these obstacles. So this environment can be represented with numbers, of course, in computer. So we can say that let's say we can represent the free space as 0, obstacle as 1, um, unscanned unexplored area is -1. Okay. So you know that the scanning the sensors for the in the 2D environment and 3D environment, we can use the lidar sensor or camera sensor or ultrasonic sensors, or combination of these. to make the map of the environment. For example, when lidar will hit, so this is the robot with lidar on top of it. So when it will hit some obstacle, it will create some points here. So let's say let hit over here. So this first hit, second hit, third hit, it will create this dot 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 over here. Okay, and when we move this robot in the whole environment, so the boundary of the obstacle will be marked with the black points, and where there is no obstacle, then that will be the free cell, a white cell. So this way we can, using the lidar sensor, we can create this occupancy grid map, and then we save that map of our environment, and later on we can use this occupancy grid map for the path planning algorithms. This is the example of the in robot operating system ROS, uh, that how the ROS can create this occupancy grid map using lidar sensor. For example, this is your robot over here. So your robot is sitting over here. So we'll do this in some ROS based labs next weeks. And this is the environment in your home, maybe, okay, and this robot is equipped with some lidar sensor, and if we move this robot in this environment, okay, and we run the mapping algorithm, so a mapping algorithm will give us this map. So this is the occupancy grid map. So what it shows, there are free spaces, there are white spaces which are free, and there are some black spaces which are occupied spaces, and maybe some gray which are not explored somehow. So once we get this map, okay, it means that now we can apply our BSF, our Dijkstra algorithm, A-star algorithm to this map information, information which is given 0, 1, and -1, and then our algorithm will draw a map between any starting node to the goal node. So once we have created this grid map, our next task is to finding the shortest path on this grid map. So as I mentioned, that there are a lot of different algorithms which use this grid map to create the shortest path on it, shortest path by avoiding obstacles. So BSF is one of them, and others are depth first algorithm. Such algorithm we are not going to explore it, but others are Dijkstra algorithm, A-star algorithm, D-star light. There are many. There is a family of the algorithms. So some of them we will study in this class. So let's apply this BSF or BFS algorithm, which now it is, we call it Grassfire algorithm, because we have some starting node and we have some goal node where the algorithm will finish, will stop. So we call it Grassfire algorithm now. So let's apply it to some example to understand how this Grassfire algorithm will work in this grid environment. So for example, we are given this grid map. So this grid map is generated by some algorithm already moving the robot in the environment and manually or somehow, or by scanning the environment. So we know we have this map already. So in this map, what we have the black and white cells. So and we can specify any starting node and any destination node within this grid. So let's say we start from this green cell, which is here, and then we give it a weight or value 0, and then there is a red cell somewhere in the environment. That is our goal. And black are obstacles. So how we can reach efficiently with the minimum distance or shortest distance or minimum energy from the starting node to the goal node. So let's apply BSF or Grassfire algorithm to this to this example. So, what it does that first it explores the neighboring nodes where it can go. So, if you see that from this green node, we cannot go up and down. We cannot go up and down because there is a black cell over there. Black means that is obstacle, we cannot go, and we also cannot go diagonally if we have the uh, 4 connectivity scheme. But if we have the 8 connectivity, of course we can go in this cell as well. But for keep the simple example, we just consider the we can go 4 connectivity scheme. So in this case, we can go only one distance to the left, or we can go learn one distance to the right from 0, and we add the new neighboring nodes uh, with a number 1, value 1 and 1. So next step, next okay, let me start. Let me call it um, okay. We call it the step 1, step 1, step 2, and so on. So in step 2, we moved one step to the neighboring nodes. In step next step, we move from the neighboring nodes to the next neighboring nodes. So let's say we take the first this leftmost neighboring node, we can move only downwards. We cannot go up, we cannot go right, and we of course we cannot go back. So we move one step further and the downside to this node, which is 2, which now we are 2 meter away, let's say 2 unit away from the starting node, to give it a number 2. Similarly, on the right side we have 1, then we can move only right side, or we can move only downside. We cannot go up or diagonal or down or left. Left is our starting node, we will not go there. So now we have had 2 more nodes with the number 2, 2, 2. Actually, total is 3, right? With the neighboring nodes. So now, then in the next step, number 4, we take these 3 nodes which are at a distance of 2 units from the starting node, and then explore further neighboring nodes. So let we start. If we start from here, we can go to this 3 node, and from this 2 we also go to this 3, and also this node we also go to this 3. And if we go to leftmost 2, node number 2, we can go only downside, and that is the 3. So now we explored 3 new nodes which are at a distance of 3 from the starting node, and this is our step number 4. If we move to the next step, we start from the current node which are 3, 3, 3, and then continue to the neighboring nodes. So next node is 4, we can move only from this node, we will move on the right side, on downside. From this node 3, which we can move on right side and the downside, and this node we also can move from right side and downside. We cannot go left side because of the boundary, and this way we continue. Continue. Next we take this 4, and we move left and right, left and so right and down. From this 4 we can move only to the right side. From this 4 we can move only to the downside, and this 4 we can also move the downside. And next we take the next step. So this way we continue this exploring our this grid environment by taking care that we cannot go in the black areas, we cannot go on the boundaries, and we are moving away from our starting node step by step, and just exploring the environment. Whenever we hit the goal node, we stop our algorithm, but somehow we cannot hit the goal node, and just to keep continue, we may not reach the goal point. So we keep exploring or expanding in all possible directions until we find the destination node. So this is the idea of the Grassfire algorithm. So once we hit the goal point, so goal node, So, we stop our exploration algorithm, and um, okay, for example, in this case we have found our let us say in some try, let us say we did many steps, let us say in the nth step, in nth step we found we hit our goal node and we stop there. We don't need to explore further because we already have reached our goal. So, next task will be to draw the path. So, draw the path. Okay, that is called the backtracking. Backtracking. Backtracking means that we reach the destination point and go back. Let me write down here. Backtracking means that draw the shortest path between uh, goal point, goal and start node. So, next we stop the exploration algorithm, and next we start the backtracking algorithm. So, how it works? So, backtracking algorithm will start from the destination node where we are currently now at there, and then it will go in the next explored nodes which are less than the number with current number. So, current number is 13, right. So, in the next the already explored nodes is 12, and 12 is less than 13. So, it will draw a point from 13 to 13 to 12. After 12, the next explored node is 11, and 11 is less than 12. So, it will continue backtracking to that node. After 11, it has two paths. It can go to this explored node, or it can go to this explored node, but if it cannot go to the 12 because 12 is already greater than 11. So, it will go to the less number. So, it means that it will go in this direction, 11 to 10. So, it will go 11 to 10 in this direction, right. It will not go in this direction because 12 is greater than 11. So, it will go to the number which is less than the current number. So, after 10 it will go to 9, of course, and at 9 it has two options. Okay, either okay, again it can go 10. No, it cannot go 10 because 10 is greater than 9. So, it will find the least number, the less number. So, it will go from 9 to 8 over here, or it is here. From 8 again it has two explored neighboring nodes which are already explored, which one is number 9, one is 7. So, it cannot go 9 because that is number is greater than 8. It will go to 7. Again go to 6, 5. On 5, when it is here, it will not go to 6 because 6 is greater than 5. It will go to the less number which is 4, and then again it go to 3, and at 3 it has two options over 3 here. It can go to this direction or it can go to this direction. Okay, from 3 it can go to 2 on the upper side, or from 3 it can go to 2 on the left side. So, both are possible because 3 is 2 is less than 3 over here. So, it can go like this or it can go like this. So, both paths are valid paths with equal distance. So, it can go from 3 to 2 this way, and then 2 to 1 this way, or it can go from 3 to 2 this way and then go to 2 to 1 on this way. So, both paths are valid. After reaching 1, it can go only one direction is left, it go to 1, go to 0, right. So, there are two paths now, one is from this path and one is this path. So both paths are valid. So it can go from like here to here, or it can go from here to here. So this is the path finally generated by the by the two algorithms. Basically, this is Grassfire algorithm, but it has two algorithms. One is the exploration algorithm. Second is the backtracking algorithm. So these algorithm will give us the shortest path from the between the starting node and the goal node. So you can apply this algorithm to any environment which is represented by the grids, and we have the starting node and end node. So let's okay, if you want, we can try this over here. So our second option is you can start from the end node as well. There is no issue, right? You can start from the end node and try to reach the starting node, or we start from the start node and try to reach on the end node. So in this case, if we start from the 0 node, okay, sorry, if we start from the goal destination node or goal node, so again we give it 0 weightage because this is a starting node, and we continue the same way as we did before, that we'll go to the neighboring nodes. Let's say the first neighboring node, there are 4, 1, 1, 1 and 1, because we are using the 4 connectivity. And after that, we explore we can go up to 2, down to 2, but we cannot go in this side because this is the boundary. Similarly, from this one we can go left and right, but we cannot go on the downside because this is the boundary. From this one we cannot go in this direction because there is obstacle, but we can go left, we can go right. From this one we can go up and down and left, but we cannot go back because that is back as our starting point. Okay. So this will, when once we reach the 2 units from the starting node, and next we continue to explore from the next node. Here we cannot go in this direction because there is a boundary. We cannot go in this direction, there is a boundary, and we cannot go backward because that is number is less than the 2. But in this case we cannot go in this direction. We can go left side, we can go down side, and same way from this one we can go left side, we cannot go down side, we cannot go back side. So this way we keep exploring. We can go, okay, this is okay, but this is not okay, and this is also not okay. From 3 we can go up side, we cannot go left side, we cannot go right side. From 4 we cannot go in this side, we cannot go in this side, but we can go in this side. From 5 we can go this side, okay, this side okay, but we cannot go this side. So this way you keep exploring the environment in all direction, also from here to here. And so this is like a fire. So fire expanding in all direction until we hit, by chance we hit the starting node or the destination node. When we hit, we stop. Okay, and after that our exploration algorithm will finish, and now we start our back propagation algorithm. As we said that we start from this, let's say the 10, we go back to 9, then go back to 8. This is also possible. Go back to 7. Okay, so this way we backtrack our path from the destination to the starting node. So this is the concept how we can implement this Grassfire algorithm to our grid-based environment, and this is the pseudocode. So let me continue next time. There is the same example. So we'll do some examples, and we'll see that how we can apply this to more complicated, bigger environments with more obstacles next time. Okay. Okay.